So the next speaker is Valeri Rubakov, and he will tell us about non-singular cosmological models with strong gravity in the past. Let's go ahead.
So here is the title, Non-Singular Cosmological Models with Strong Gravity in the Past. My collaborators on this topic are Yulia Ageyeva and Pavel Petrov. We have published several papers already on this topic. So let me go to introduction first and point out that, first of all, I'm going to discuss homogeneous, isotropic, and spatially flat universe throughout this talk, without, much of motivation for special flatness. But we know that the universe is essentially spatially flat. Now, what I'm going to discuss are non-singular cosmological models, namely two of them. One which is called bounce. You start from contracting universe, slowly contracting universe, contracting instead of expanding, slowly contracting universe with negative Hubble parameter. Then contraction speeds up, energy density increases. Nothing particularly weird about that, but the point is that at some point you assume that the contraction terminates and one has instead expansion. So the behavior of the Hubble parameter is like here, and today we are at late expansion stage. So the key thing here is bounce, the moment of time when contraction terminates and expansion begins. Another non-singular solution, non-singular cosmology, is what's called genesis. You assume that the universe starts from Minkowski empty space with zero Hubble parameter. Slowly, the energy density builds up. The universe starts to expand. Expansion accelerates. And in both cases, you have to make sure that the end is conventional hot epoch or inflation, maybe. Now, the motivation for considering these non-singular cosmologies is, of course, the first thing is curiosity. It's always nice to have alternatives to very well known and very well thought of scenarios like inflation. The thing is that these non-singular cosmologies, by definition, do not have initial singularity, which is a nice feature, so that you can follow evolution from the beginning to the end. If you think about solutions of conventional problems of hot universe, of hot Big Bang theory, like horizon curvature, then basically you take them out to very early times and make an assumption that you start off with something very similar to what we have now, but either very slowly expanding or very slowly contracting. But technically, it's sort of useful because you have solved the horizon problem, and this means, in the sense that we live in a causally connected region of the universe today, and this means that, in principle, we have a means of generating cosmological density perturbations in these scenarios by causal physics. Now, one more bonus, which is not emphasized often, is that in both cases you have very long prehistory, where matter energy density is essentially zero, and the universe is, empty of matter, and this seems to be a necessary condition for relaxing the cosmological constant. If you start off with non-zero cosmological constant, then of course the picture is somewhat different. You have a finite rate of contraction, or say in the bouncing universe you have finite rate of contraction, but you have enough time to relax the cosmological constant to a very small number. That's one of the prerequisites. I think you need very, very, very long time to realize the cosmological constant. Now, it's not. There are, of course, drawbacks, and one of the drawbacks is you have to work hard to generate the power spectrum of scalar perturbations in your theory, and this has not been quite solved yet. Okay, so let's try to construct the bouncing and genesis scenarios, models. However, there is an immediate obstacle, which is called the null energy condition. If the special curvature is negligible, which I assume, both bounce and the genesis need matter that violates the null energy condition. In this cosmological context, this null energy condition means that effective pressure is greater than minus energy density, and instead you must have pressure which is less than minus energy density. And the reason, for example, is that if you have the Friedman equation, one of the Einstein's equations for homogeneous isotropic specially flat universe written here, and for matter that does not violate the null energy condition, the right-hand side is negative, so that the Hubble parameter always decreases, and that's not what we want, because both in bounce and genesis cases, there are epochs when the Hubble parameter actually increases. And moreover, if you do not violate the null energy condition, then Penrose's theorem for expanding universe tells you that there was an initial singularity, and we want non-singular cosmological models. Right. Now, we know that in conventional field theories, the null energy condition is not violated, provided that the Lagrangians involve first derivatives only. That's known for a long time. So if you want to have a null energy condition violating theories, then you have to do something better. Indeed, if you look at conventional field theories, then there are two possible effects. One of them necessarily shows up is that you either have ghosts, meaning that energies of particles of excitations are negative and arbitrarily high for high momenta, meaning catastrophic vacuum instability due to pair creation of these ghosts. Or you have gradient instabilities where the energy is imaginary and the perturbations of fields increase exponentially, which is also catastrophic because, again, the energy of an excitation can be arbitrarily high for high momentum. So you do not want ghosts, you do not want gradient instabilities, and you can't avoid them if you consider conventional field theories with first order Lagrangian with first order derivatives. However, it is not necessarily true that the field theories, healthy field theories, have Lagrangians with the first derivative only. There is a set of scalar tensor theories in which Lagrangians have second derivatives, and nevertheless, the field equations are second order. And this avoids Ostrogradsky ghosts because if you have high derivative equations of motion, then typically you have a ghost, not necessarily again, but typically often you have Ostrogradsky ghosts. They're precisely the negative energies, excitations with negative energies. This is not necessarily true. There are models with higher order equations of motions without the Ostrogradsky ghosts. But I'm going to stick to simpler set of theories, namely theories where the field equations are second order, even though the derivative, the Lagrangians contains second derivatives. And these are known as Hromdeski theories. The simplest example of Hromdeski theory I will show more general theory later on. But the simplest example, which I invite you to study, is shown here, where you have the usual Einstein-Hilbert term. In the Lagrangian, you have conventional, more or less conventional kinetic term, and in the with first derivatives only, f, and you also have the term with box pi, meaning that you see that there are second order derivatives in the Lagrangian. But when you calculate the equations of motion, lo and behold, you find that the second derivative, third and higher derivatives in the Lagrangian cancel in the equations of motion cancel out, and the equations of motion are still second order. And then you have more freedom here, and you immediately can construct explicit examples of stable knowledge conditional relation. However, things are not as simple, because if you want to construct cosmology that starts from minus infinity to plus infinity in time, formally speaking, then you get problems, which were first observed explicit by when people try to explicitly construct models of this sort. They figure out that you always have gradient or ghost instability in the theory. Not at the time of the most interest for you, like say at the time of bounds, but at some point at some time in the evolution. And this actually has been formulated as a no-go theorem, saying that in Hordesky theory, you sort of can't go about that. You always have gradient or ghost instability. With caveats, of course, any theorem has its assumptions, and that's what I'm going to discuss later. So how does the no-go theorem obtain? First of all, this is the form of general Hordesky theory. You have our familiar terms, f and k, with box pi, but there are also two other terms, 4 dimensions, which contain arbitrary function of pi and d pi square, which is x, and these particular combinations of the second order in derivatives terms. Okay, so there are G6, G4, and G5. Okay, and x here means the derivative with respect to x. So we're dealing with modified gravity. I'm going to work in the Jordan frame all the time. So here is my Lagrange. Now, no-go theorem obtains when you consider perturbations about homogeneous and isotropic solutions. Suppose you have homogeneous and isotropic solution to your theory, like bounds or genesis, and you consider perturbations about these solutions. In the unitary gauge, where the scalar, which is here, this pi, is not perturbed, this is unitary gauge, all perturbations are contained in metric, in transverse tensor part Hij, and zeta, the scalar part. And after some work, you find unconstrained action. The lefts and shifts, as usual, are non-dynamical variables which are integrated out. Once you integrate them out, you're left with perturbations for scalar and tensor sector of the usual sort. These are, there are no second order derivatives whatsoever, and that's one of the manifestations that your theory doesn't have second order equations of motion. So these are conventional Lagrangians, and the whole point is the signs of the coefficients in these Lagrangians, right? If you want a stable background, then all these coefficients must be positive. Okay. Now, question is, are they positive? You to see whether they are positive or not, you calculate these coefficients here in the scalar sector, in the scalar sector and in the tensor sector. They are given by pretty horrible expressions, which I wrote once for, in particular case, when this G5 Horndeski function is equal to 0. Otherwise, they are not, you can't put them on the transparency. So all these coefficients here are functions of your Lagrangian functions entering the Lagrangian and their derivatives. Here is the explicit expressions for them. You're not supposed to look into these expressions here. What's important is that the parameter theta here, which is in the denominator everywhere, is a combination of of the Lagrangian functions. So that for non-singular solution, this theta is finite, maybe 0, but not infinite. And the main thing to mention is that the expression for the coefficient of the scalar perturbation here involves the tensor perturbation coefficient and the total derivative of psi. Here it is written that the combination of scalar and tensor coefficients, which must be positive, is a derivative of psi with respect to time, and psi, as you can see, is a function that never vanishes, never crosses 0. Okay, this is the tensor coefficient, and theta is a combination of your Lagrangian functions, which is not infinite. So psi never crosses 0, and that's impossible, because if you integrate the equation of psi, then you get this integral relationship. And if you assume that, if you think that your f, the coefficients of scalar and tensor sector are positive, and your scale factor is finite, doesn't go to 0 as time goes to minus infinity, like in Genesis or bounce case, when the scale factor either goes to a constant or to infinity, then this integral is divergent both at the lower limit and at upper limit. And this is impossible, because if you write down psi minus psi of 0, say, as this integral, then you immediately find that since this integral is divergent on the upper limit, then this psi goes to plus infinity as time goes to plus infinity, and likewise psi goes to minus infinity as time goes to minus infinity. So psi crosses 0, which means that you have singularity. Okay, so the argument works, in fact, in general Horndeski theory, in the Horndeski theories with multiple scalars, Horndeski or otherwise. You can add meta, nothing else helps. Now, let me just enumerate the ways out. One way out is to go beyond Horndeski, and that's the theories in general called host theories with higher derivatives in the equations of motion, but still without any ghosts or gradient instabilities. You can, this is a possible way out. However, these theories turn out to have their own problems with superluminarity in particular. So this may or may not be a way out, actually. Second possibility is that, in fact, the integral here is convergent on the at minus infinity. at the lower limit. Okay, because then our no-go argument doesn't work. Our argument works if these integrals are divergent both at plus and minus infinity. At plus infinity, this means today, this is huge integral, so plus infinity is not useful, but minus infinity can be useful. And you may think of a theory in which the integral of interest is convergent at the lower limit of integration. Is that possible? Well, there are several cases when this integral is convergent at the lower limit of integration. For example, you can start, instead of Minkowski space for genesis, you can start with de Sitter space. And then this integral converges because a goes to minus infinity at large negative times. This seems to do the job, although this is not quite the genesis. You start already with de Sitter space. That may be an option, actually. Another option is that instead of that this integral converges because a of t tends to 0 at large negative times sufficiently rapidly, like here, for example, as Power law. As time goes to minus infinity, this is Power law, integral is convergent. Hubble parameter and its derivatives vanish at large negative times, so that you appear to deal with nearly Minkowski spacetime in the beginning. That's sort of looks similar to genesis. However, it was realized that precisely this property means that your geometry is past geodesic incomplete. Our particles were in Jordan frame. Particles live in this in the universe with this scale factor a of t, and this is precisely the condition of geodesic incompleteness of your theory. So you have sort of singularity, even though mild singularity, but still this is not an acceptable geometry. So what I'm going to concentrate is instead of sending the scale factor to 0, I'm going to send the coefficients of the scalar and tensor perturbations to 0. That sounds weird because these are coefficients of the scale of the zeta dot squared, zeta di, zeta squared, etc. And these they are tending to 0, and these are effectively Planck masses, right? Scalar and tensor Planck masses squared. So what I am doing is I send the effective Planck masses to 0 at minus infinity in time. And that sounds pretty weird because this means that gravity becomes a strong force, right? I send my effective Planck masses to 0, gravity becomes strong force. And the immediate danger is that the theory becomes strongly coupled. And what follows, I will be considering an example of this sort where all these coefficients are inversely proportional to time, to some positive power as time goes to minus infinity. So indeed, they tend to 0 rapidly as time goes to minus infinity. And then, of course, this integral is convergent for mu greater than a half, and the no-go theorem doesn't work. But there is a danger of strong coupling. Now, immediate question is, can you trust classical field theory description of the cosmological evolution? I have a cosmological evolution. Is it going in the classical field theory regime, or you have to deal with quantum gravity? To understand what's going on, you have to compare the classical energy scale, which is inverse of the time scale of the time, which goes to 0, by the way, as time goes to infinity, to minus infinity. And then you should compare this classical time scale with the strong coupling scales, which should be obtained by looking at the interactions of my perturbations, zeta and Hij. So if I find that the strong coupling scale obtained from interactions, inferred from interactions of the perturbations is much greater than the classical energy scale, then I'm in good shape. My strong coupling scales, my effective Planck mass is greater than 1 over T, the classical time scale, classical energy scale. That's more or less the same as today. We have Planck mass, Planck scale, Planck mass, and we have the Hubble parameter, and the Hubble parameter is much less than the Planck mass, so we are in good shape. We can treat our classical, expansion today in classical field theory framework. Similarly, I want to do the same at minus infinity in bouncing or genesis models. Let me give you an example how this happens. This is not at all the whole story, of course. Let me concentrate on the tensor sector and write explicitly the cubic interaction in the tensor sector. Here we go. And in fact, what happens is that coefficient of the cubic interaction is actually the same as the coefficients in the quadratic part. And that's, again, familiar. In gravitational case, you have overall m Planck squared in the whole action, right? So all terms, both quadratic and cubic and higher order, are in general relativity, they are proportional to one and the same parameter m Planck square, and here they are proportional to one and the same function f. So what are the strong coupling scale? We have to canonically normalize my perturbation Hij, that's what is that here, and obtain that in terms of canonically normalized perturbation, my Lagrangian to cubic order has this form, and you have dimension 5 operator, which with the coefficient 1 over square root of f in front, and you immediately infer the strong coupling scale here. Strong coupling scale is the square root of f, which is minus t to minus mu, right? It goes to 0, but if my mu is less than 1, then the strong coupling scale goes to 0 slower than the classical energy scale. So as you go backwards in time, the quantum strong coupling scale becomes higher and higher compared to classical expansion rate, and you're in good shape. So overall, you have healthy bound stage in this case within classical field theory at weak coupling. Now, of course, this is not the whole story, because you have not only tensors but also scalars. You have not only cubic but also higher order terms in the interactions, and you have to work hard, relatively hard, to figure out the energy scales coming from various sort of perturbation theory, but the outcome is the same. If my parameter mu, which governs the behavior of these coefficients f and g, is less than 1, then the strong coupling scale is always higher than the classical energy scale t minus 1. And another example is cubic interaction of the scalar perturbation, which is written here. It contains 3 derivatives now, the time derivative and 2 spatial derivatives, and then you again do the canonical normalization and obtain the strong coupling scale of this sort, which is again higher than the classical scale when mu is less than 1. So all this goes through order by order in perturbation theory. So if my mu is less than 1, then my classical field theory treatment is legitimate. Even though gravity...
30 minutes. You just had
Sorry?
30 minutes. You just had 30 minutes.
Okay, so I'm coming to my to the end. So this happens in large regions of region of parameter space. So the whole scenario is viable, and the picture we have is quite non-standard. You start off with the universe with very low quantum gravity scale, which goes to minus infinity to 0 as time goes to minus infinity. So the beginning is the theory with very low Planck mass, but expansion is very slow. So this is not the classical treatment is consistent. All the scales in the standard model are above the strong coupling scale, meaning that gravity is actually the strongest force here. And this construction works both for genesis and bouncing universe. So you can now construct complete cosmologies by what is called inverse method by Ijast and Steinhardt. I would call it intelligent design. You choose your functions in the Lagrangian in such a way that you get your favorite behavior of the Hubble parameter, like here for bounds. You choose you choose your Lagrangian functions in such a way that everything is fine, and furthermore, at plus infinity in time, you end up with the conventional general relativity plus usual massless scalar field, which is called kination stage, just the universe filled with massless scalar field that drives the expansion of the universe. And you cook up Lagrangian functions in such a way that your field equations are satisfied, stability conditions are satisfied at all times. And as I told you, classical field theory is valid at early times. So all this can be done. I'm not going to go into any detail here. And also you might be worrying that in these theories, in principle, you can have superluminal propagation of perturbations. You add another condition that propagations do not propagate superluminally here. And here are the examples, a couple of examples. This is the bounds. You see, this is the Hubble parameter. This is bounds. The Hubble parameter is negative, becomes more and more negative. At some point, it crosses 0, becomes positive, and then you have the kination stage. And these are examples of scalar and scalar parameters, scalar coefficient here, which is positive, as we need, and the speed of scalar perturbations, which is less than 1, so that you don't have well, first of all, this is positive, meaning that you don't have instabilities. And second, it's less than 1, you don't have superluminal propagation. Same with inflation. You can also have, after the bounce, you can also have inflationary epoch if you want. This is slowly changing Hubble parameter, which flattens out, and you have inflationary stage. You can do that as well by choosing appropriate function. You see, you have a functional freedom in your Lagrangian, therefore you can play these games, and all the time you have stable and subluminal perturbations. So let me conclude. It turns out that constructing complete non-singular cosmologies with bounds or genesis is actually difficult. You first of all need, in the scalar tensor theory, you need non-trivial kinetic and gradient terms. You need, well, if you do that, then the bounce epoch itself and the early genesis epoch itself are not particularly problematic. However, if you want the complete cosmology, then you have an instability at some point in the evolution. One possible way out is that you have strong gravity in the past, effective Planck masses tend to zero at minus infinity in time, and the gravity is the strongest force. Sorry, strongest force. There is misprint here. It's the strongest force. Nevertheless, the classical field theory treatment of background evolution is legitimate in a certain range of parameters, and we have constructed healthy bounds and genesis cosmologies in this framework. Now there is a remaining issue, maybe more than one, but one remaining issue is that you also need realistic scalar and tensor perturbations generated in these scenarios, and it's not clear for the time being whether you can do them easily or you have to invent some, additional fields, additional spectators or something to produce scalar tensor perturbations with required properties. Thank you.
Okay, thank you very much for this very nice talk. Are there any questions? I can see Richard Woodard. Please go ahead.
Okay, thank you. Thank you for this talk. This question is relevant to the first part of your talk, trying to evade the problem with the violation of the weak energy condition. I wonder if there's anything to be gained by the fact that quantum corrections can sometimes give violations of the weak energy condition on cosmological scales.
Yeah, there is this line of thought. Even though I'm not quite, I was trying to keep within the classical field theory, and to me, relying upon quantum corrections for the spatially flat universe is something which I would try last. If nothing works, then I would rely upon quantum corrections.
Okay, thank you, Arkady.
Okay, kind of trivial questions or by beginners. So for your scenario, do you need this high derivatives, or it just you mentioned that and you're not using this having high derivatives in action? Or
yes, I absolutely need high derivatives in action. That's absolutely
necessary. Then my kind of maybe indeed kind of out of weakness technical question, that if you have this high derivatives, let's say I'm quantizing this theory, right? Then normally, we are having coordinate to count degrees of freedom. We have canonical coordinates and conjugated momenta, right? Mm-hmm. And it goes, conjugate moment goes instead of first derivative, and in this way you have Hamiltonian, for the system. When you have these high derivatives, then and you are trying to do a similar procedure, counting, conjugated pairs, how it goes in this case.
Well, that would be a long story, but let me just give you a very short answer. The very short answer is that in this particular class of theories where field equations are second order, even though you have higher order terms in the Lagrangian, the field equations are second order, okay? And this is a peculiar situation where essentially there are sort of constraints and degeneracies when you start doing the standard Hamiltonian treatment. There are degeneracies which show that in fact you do have exactly one scale degree of freedom. Normally, if you have more than one derivative in the first derivative in the Lagrangian, you have extra degrees of freedom, right? That's what you're.
Yeah, that's why I'm asking, right? Indeed.
Yes, but here this is not the case. The number of degrees of freedom remains one for scale.
Yeah, but then it means that these high derivatives, in certain sense, are kind of no, in certain way, it's like effectively it is a series with first derivative, but it's written in this way, right?
No. You can't make any transformation like, you know, the integration by parts or something like that.
Yeah. No, right? But then it means that still at the end, so you still can construct Hamiltonian formalism at the end of the day, right?
Yes. With one degree of freedom.
Yeah, I got the point. Yeah, but I mean, okay, I understood. Okay,
Yeah, you can do the Hamiltonian treatment. It's tricky because of various degeneracies.
Yeah.
Once you do that, you are left with Hamiltonian treatment with one degree of freedom, which is
thank you.
Almost conventional.
I see.
In the end, when you have to, you know, you have to do all the well, you have to be very careful. That's
okay. I will try.
Okay, next question is by Alexander Zakharov.
Okay, do you hear me? Valeri, do you hear me?
Yes, if you speak somewhat louder.
Oh, okay. You consider cosmology as a way to find suitable alternative for general relativity. But also people investigated black hole-like solution for Hardetsky, beyond Hardetsky. And meanwhile, observers got some constraints on parameters of this kind of theories. What do you think about perspectives?
Well, I think it's an interesting endeavor. It's not my endeavor. It's not what I'm doing. I'm doing very early universe. But in principle, it's an interesting approach to see whether the general relativity is exact theory or it has additional ingredients like, you know, Hordesky or something like that, scalar tensor. So it's an interesting story. My own expectation is that in our world, in our stage of the universe, I think general relativity is going to be perfectly valid, but who knows? If it is not, this will be the greatest discovery of 21st century.
Okay, thank you.
Okay, Sebastian Self next.
Yeah, so I was wondering about your no-go theorem. Can you postpone the problem to the future so that you have like past completeness, but you get, for example, an instability at some point in the future? Is that possible?
Yes, that's possible. But the problem is that you always have an instability. So, to me, we are presently in the infinite future. So the instability still should be in the past.
So it's not possible to put the instability in our future.
In our future, I doubt. I strongly doubt, because we do have general relativity with possibly small corrections today. Therefore, I can't, you know, do very much today.
Okay. Yeah. Thank you.
Okay, next, Alexander Wickman.
I actually wanted to ask you partially what Sebastian asked, because we had this example in G-bounds where basically the evolution would start from a singularity, but in a collapsing universe, basically from infinite strong coupling, then bounce, and then evolve to normal radiation domination stage. This normal, practically almost normal GR in a radiation dominated stage. So in some sense, so Sebastian, if for you future is radiation domination, then it's okay. So it's possible to have really singularity only in the let's say past. On the other hand, it's possible to have it only in the future as well. That's possible. Just invert these dynamics. But I'm more interested.
No. If future, we are talking about future of our universe, then I disagree.
Oh, sure, of course, but that's a different question because that's not covered by the theorem, right?
Mm-hmm.
But what I'm wondering, so what do you think? So what is your new development on this superluminality? Because somewhere in the phase space, this stuff is still superluminal. So basically,
I'm not quite sure. With this particular sort of theories, what we have checked is that around the solutions that we have, there is no superluminality whatsoever. And we didn't go very far away from this trajectory in the phase space of cosmological solutions, because what we actually need are sort of the Lagrangian functions at this trajectory and nearby.
Right.
With respect to x. So we didn't check if we can. This is the very complicated issue, I think, to try to construct a theory which is subliminal everywhere in the configuration space. But I don't think that it's impossible. But I don't know the answer, so it's
right. It's very hard, especially as far as I remember, the first paper by Nima, Sergei Dubovsky, Alberto Nicoles, and Riccardo Ratazzi. When they discussed this impossibility of UV completion, they were criticizing DGP on the grounds that basically static configurations will have superluminality. But of course,
yes,
there is an infinite.
I agree that you have to avoid superluminality better, otherwise you are in trouble with these people, Nima and company, Dubovsky, Ratazzi. But I agree that you have to be careful, and if you want the complete theory, then you have to ensure that it's subliminal everywhere in the configuration space.
Which is super hard to prove.
But that's a hard job, because for that you need all your Lagrangian functions to be defined everywhere, and you have to know what are they very far away from your solution.
Yeah. Would be great to have a notion of how different effective field theories are close to each other, in which sense they're distant, how to basically make the distance between different AFTs. That would be fantastic. And if I may, I can comment on what Arkady was asking, because importantly, the series you mentioned at the beginning, so this whatever, braiding or whatever, with this box phi coupling to kinetic term, the important thing is that they're very similar by structure to GR, namely the second derivative enters only linearly. And that's the key property, like similar in curvature. There is second derivative, but it's only linear there. So therefore, there is no need for all this complicated additional momenta or whatever. Basically, what you need is a boundary term.
Not quite. If you consider G4 and G5, then...
Oh, no, of course. What I meant is what I like. is the simplest one.
That's simpler story, but for G4 and G5, it's more complicated.
Oh, G4 and 5, of course, it's much more complicated. Thanks a lot.
Okay, now the last question for this talk by Jae-Hyu Chun.
Yeah, thank you for the talk. It's a quick question. So your talk reminds me that there's another branch of bouncing community, which is about matter bounds and equibrotic bounds. So in their models, they can...
Say it again, about what?
Matter bounds and equibrotic bounds. So that is essentially an alternative to inflation, in the sense that they can generate almost exactly scale invariant for a spectrum. And it has been argued to be an alternative to inflation. So, and also their model contains some scalar fields to construct the model. So my question is that since the theory contains several functions that you can turn, so do you think is it possible to mimic such kind of particular bouncing model in that scenario?
Well, in the first place, I should say that what we were concerned is the cosmology where your bouncing stage, both bouncing stage and the stages before and after, are described self-consistently. So if you are considering, for example, the equibrotic bounce, then the contracting stage is clear. However,
yes.
the problem there is to get out of the contraction stage and go into the expanding stage.
That's
and then
right.
You either have to rely upon some miracle, or, in general, the problem is that you don't really know how to connect contracting and expansion stage. That's the first issue. So our point was to do within the classical field theory, to do complete cosmology with bounds without any instability in there. Now, whether or not you can mimic matter bounds or periodic bounds, that's precisely what we are doing now. What we are
Okay.
now. I mean, not in this language, but it appears that somehow the geometry, effective geometry for scalars and tensors is, of course, not the Jordan frame geometry, because my coefficients depends on time, right? So here are the Lagrangians, right? And these coefficients G and F, they all depend on time. So effective geometry is not for perturbations, for gravitational perturbations. This effect is not the geometry in terms of the scale factor A, which we have. It's not Jordan frame geometry. And so you might think of using this property to generate flat or nearly flat power spectrum of density perturbations. But that's not what we have done yet.
Okay, I think we should be moving on. Let's thank Valeri again.